first example, we're going to use a system that has one solution. We already can identify what this solution is from the graph of the equations as 1, 4. So we know that when we plug in x and y into both of these equations in the system, that this point is true. It satisfies both equations. Now we're going to focus on how we can use the elimination method in order to find the solution. So I'm going to rewrite this system underneath step 1, which is where we're going to combine and eliminate one of the variables, hence why it's called the elimination method. The reason why we can use the elimination method is because in our system, both equations have the same variable with the same coefficient but opposite signs. So we have the perfect conditions to apply the elimination method in this example. We have the same variable, y, we have the same coefficient, 1, and we have opposite signs for both of the equations in the system. So that being said, we can combine these two equations. We're going to combine our like terms. So we'll get 7x plus 0y, which equals 7. So anything times 0 equals 0. So we don't actually have to write plus 0y. Now we have an entirely new equation that we're working with, and it just has one variable. So we have 7x equals 7, and we can all solve an equation for one variable. So now we're going to divide both sides by 7 to isolate the variable x, and we get x equals 1. Now after we've eliminated a variable and we found our first coordinate, we have to find the other coordinate. We have to find y in this case. We already know what x is, so we're going to plug in x into one of the original equations in order to find what y is. So I'm just going to take the second equation here, 4x plus y equals 8. I already know what x is, so I'm going to plug in x, which equals 1, into this equation. And now I can solve for the other coordinate, which is y in this case. So 4 times 1 is 4, plus y equals 8. And now we can use this new equation in one variable in order to find y. So 4 plus y equals 8. We can subtract 4 on both sides. So we'll have y equals 4. So I found x and I found y. Now all that's left is to write our solution as a coordinate. And we know that our solution's correct because we found our solution earlier on, before we even started using the elimination method, from the graph of 1. So remember, for the last example, I said it was really, really important to make sure you had 3 specific conditions in order for you to use the elimination method. You have to have the same variable in both equations. They both have to have the same coefficient, but they have to have opposite signs. So right, those are the 3 things we need. Right now in this system, we don't have those conditions, but we can make them. So we're going to take one of our equations and we're going to multiply it by the least common multiple in order for us to eliminate a variable. So for the 2 lines in the system, I've decided I want to eliminate y. So that way I can solve for x and then go back and solve for y later. So I'm actually going to take the second equation in the system and I'm going to multiply that entire equation by 2. So if I'm multiplying every single term in the equation by 2, I'm going to have to use the distributive property just to show that I'm multiplying every term by 2 and make sure that I don't forget anything. And then I'm going to rewrite the first equation that I didn't change at all. And now I have a new second equation in this system. Now I have those perfect conditions that I need to use the elimination method. I have the variable y in both equations. They have the same exact coefficient, and the coefficients have opposite signs. So the perfect three conditions. Now I can combine these equations to eliminate. So combining like terms, we have 4x plus 2x, which is 6x. Negative 4y plus 4y is 0y, or just 0, and I don't have to write that. And then negative 8 plus 2 is negative 6. So we have an equation in one variable. Now we're going to solve this equation for x. So we'll divide both sides by 6 to isolate x, and we'll get x equals negative 1. So now that I found x, I'm going to take x, plug it back into one of the original equations in order to find my y variable. So I'm choosing to use the second equation in the system. I'm going to substitute x in place with negative 1. And now I can solve this new equation in order to find y. So I'm going to add 1 to both sides, and then divide both sides by 2 to isolate y, and I'll find that y equals 1. So then the last step is to just write your solution as a coordinate. So x is negative 1, y is 1, and that's my final answer. So for example 3, instead of multiplying just one equation, I'm actually going to have to multiply both equations in order to get my perfect conditions. So you have to decide which variable you want to eliminate. In this case, I've been having a lot of fun eliminating y, so I'm going to do it again. I'm going to eliminate y, so I have to decide now, what am I going to multiply line 1 by? What am I going to multiply line 2 by? So the coefficient for y in line 1 is negative 2, and the coefficient for y in line 2 is positive 7. Now the least common multiple of those two numbers, if we ignore the signs for just a second, is going to be 14. So I need to multiply the first equation by positive 7 and multiply the second equation by positive 2. When we multiply the first equation by positive 7, we're going to have negative 28x minus 14y equals 98. Now for the second equation, when we multiply everything by 2, we're going to have negative 20x plus 14y equals negative 50. So we've created the perfect conditions that we need in order to use the elimination method. We have the variable y. Y has the coefficient 14 in both equations, and we have opposite signs appearing for that coefficient in both of the equations. Now we can combine these. We're going to have negative 48x equals 48. And if we divide both sides by negative 48 to isolate our x, we are going to get x equals negative 1. So we found one coordinate. Now in order to find the other coordinate, we're going to take one of the original equations. We're going to go ahead and use the first one. And I'm choosing the first one because it has the smallest coefficients. Instead of working with large numbers like negative 10, 7, and negative 25, I'm going to work with smaller numbers, negative 4, negative 2, and 14. So I'm going to plug in negative 1 where I see x in my equation because we already found that x equals negative 1 in this system. And again, now I just have an equation with one variable, which is y. So we're going to solve this new equation that we have for y. So we're going to multiply. Negative 4 times negative 1 is 4. And then we'll bring down everything else in our equation. And then we'll isolate that by subtracting 4 on both sides so that we have negative 2y equals 10. And lastly, dividing both sides of the equation by 2 in order to get y equals -5. Lastly, we have to remember to state our solution. So we have to write the solution as a coordinate, where x is -1 and y is -5. And that's the final answer. Now, the first 3 examples that we looked at all graphed as having one solution, 2 lines intersecting on a coordinate plane. But now we're going to look at what happens if you are dealing with a system that's going to have no solution and what that looks like algebraically, as well as if we look at a system that has infinitely many solutions algebraically. So when we look at this system, we don't have perfect conditions for using elimination. We do have the variables showing up in both equations in the system, but we don't have the same coefficient for a variable. We don't have same coefficient with opposite signs for a variable. So we have to manipulate one of the equations to give ourselves those perfect conditions. Never forget those perfect conditions. All right, so I'm going to eliminate y. So I'm actually going to multiply the first equation in this example because I see the coefficient for y in line 1 is 1. So it's going to be the easiest variable for us to get rid of. We just need to look at the coefficient for y in line 2, which happens to be 2. So to have my perfect conditions, I'm going to have to make the coefficient for y in line 1 equal to -2. So I just have to multiply the entire equation by -2. And I'm also going to draw my arrows so that I remember I need to distribute that to every single term in the equation. Now my new equation for line 1 is going to be -6x minus 2y equals 4. And I didn't change anything about line 2, so I'm just going to rewrite that below the new line 1. I have those perfect conditions, and I can combine the equations, but when I combine them, you're going to see that we're going to have 0 on the left-hand side, and we have 14 on the right-hand side. In no world is 0 equal to 14. It's never going to happen, right? So because algebraically, we're not getting the same thing on both sides, and both variables have eliminated from our system, we know that it's no solution. So this will graph as 2 parallel lines that never intersect going on forever. Algebraically, your variables have completely disappeared when trying to solve it, so that you know it is no solution. This next example is also going to require us to have to manipulate our equation so that we have our perfect conditions. I don't know how many times I can say it, you can say it with me. Same variable, same coefficient, opposite signs. It's really that simple. In this system, we're going to have to be extra careful because our variables aren't lined up. Sometimes you'll see something like this where they're trying to trick you. So I'm going to rewrite the second equation, just rearranging my terms on the left-hand side so that I have x first and then y second, just so there's some consistency in the work that we've been doing. Now I'm just looking over at line 1 and I'm going to eliminate y again. Why are you surprised? In this system. So I'm going to have to make the coefficient for y -3 because the coefficient for y in the second equation in the system is +3. So for those perfect conditions, y, same coefficient, opposite signs, it's got to be -3 in order for us to eliminate it. So I'm going to multiply every term in the first equation by -3, just so that the coefficient for y will be -3. So my new line 1 is going to be 6x minus 3y equals -3. So I can combine the equations now in this system. Now that I've lined up my variables, lined up my x's, lined up my y's, lined up my constants, and we're going to get 0 plus 0 equals 0. Now we know that is true for a fact. 0 equals 0. So we know we're looking algebraically at a system with infinitely many solutions. And then if we look down at the graph, we'll see that these graph as just one line on a coordinate plane, which means both of the equations were exactly the same. And that's how you know you're looking at a system with infinitely many solutions when you're solving it with the elimination method. Now for our last example, let's look at a word problem. Gregory's Motorsports has motorcycles and ATVs in stock. The store has a total of 45 vehicles that together have a total of 130 wheels. Find the number of motorcycles and the number of ATVs. So since we're looking at a word problem, and fortunately we're given the equations in the system that'll help us solve for our unknown variables, we first just need to define our variables so that we know what we're solving for. So we already know we're going to be looking for M and we're going to be looking for A. But what are the things that we're trying to find from the word problem? The word problem tells us to find the number of motorcycles and the number of ATVs. So we're going to let M equal the number of motorcycles, and we'll let A equal the number of ATVs. So for this system, you're going to have to decide what variable you want to eliminate. I'm going to eliminate M. So I see that the coefficient of M in the second equation in the system is 2. So for the first equation in the system, I need the coefficient to be -2. That way we get the perfect conditions. I know you all said it with me. I'm going to distribute that -2 into the parentheses. So I'm going to have a new equation in the system. Now it's going to be -2m minus 2a equals -90. And I didn't change anything about the second equation, so I'm just drawing the arrow so that you see that I'm just rewriting exactly what it is to the right of it and under that new equation that we manipulated. So after doing that, we can now combine these equations. The variable that we're eliminating is m because -2m plus 2m is 0. -2a plus 4a is 2a, and that equals 40. So now we have an equation in one variable and we can solve for a. So to isolate a, we need to divide the left side of the equation by 2. And whatever we do to one side of an equation, we have to do to the other side to maintain balance. So 40 divided by 2 is 20. So we found the number of ATVs. Now we're going to use that and one of the equations from our original system of equations in order to find the number of motorcycles. So the simplest equation, it's the equation that doesn't have a coefficient for m, is the first equation in the system. So we're going to substitute the value of a into this equation. So we have m plus 20 equals 45. We'll isolate m by subtracting 20 on both sides, and we'll get that m equals 25. Now, because this is a word problem, our solution needs to be tailored specifically to the word problem. So I'm not going to write it as a coordinate, but in this case, I'm going to say the number of motorcycles equals 25, and the number of ATVs equals 20. Thanks for watching, guys. If you have any questions, feel free to leave them down there in the comment section below. Don't forget to like, share, subscribe, and we'll see you next time.